In Lesson 3.2, we have some more definitions to understand. A path on a graph is how we get from one vertex to another. Vertices and edges can be repeated in a path. On this graph, an example of a path would be going from A to B, B to C, C to D, D to E, E to B, B to A, and A to C. I could write this as a path and say that the path is simply listing all of the vertices that it touched in the order that it reached them. So the path is ABCDEBAC. A simple path is a path where no edges are repeated. Vertices, however, can be repeated. So on the graph above, an example of a simple path, AB, BC, CD, DE, and EB. So the vertex B was repeated, but none of the edges were reused twice. We would describe that path simply by the letters of the vertices that it connected, A, B, C, D, E, and back to B. The distance between two vertices is the length of the shortest path joining those vertices. On this graph, if we look at the distance from A to E, we can imagine that there are multiple ways of getting there. We can go from A to B to E. We could go A, B, C, D to E. So there are different routes that we can get there. When we write out the distance, we use the form small letter d, bracket, and then the two vertices which are of interest to us that we're measuring the distance between. In this case, we can say that the distance from A to E is 2, because there are two edges joined in the process of getting from vertex A to vertex E. Similarly, the distance from A to C would be 1. And using the same form, we would say distance between A and C is equal to 1. Try this question on your own. On the graph below, name a path, name a simple path, identify the length of the path specified, name a simple path with a length of 4, and then determine what is the distance between C and A and what is the distance between A and D. Let's start with the first one. It will be fairly straightforward because we can choose whatever path we wish, and so we can say the path is AB, BC, CD, DA, AF. That is a path. We write that path in the form just by identifying all of the vertices. So we go A, B, C, D, A, and E. It is actually coincidentally also a simple path. Another simple path might be EB, BC, CD, DA, AF, FE. Again, we have to write that out in form. We go E, B, C, D, A, F, E, B. To determine the length of the specified path, DAB, EFAB, we can certainly draw it on our graph, starting at D, going to A, going to B, going to E, going to F, going back to A, going back to B, and that's our path. The length of this path we can calculate fairly simply by looking at the number of vertices and subtracting 1. Here we've got 7 vertices, so the length is 6. Now we're asked to name a simple path that has a length of 4. That shouldn't be too difficult for us to do. We can start at any point. 1, 2, 3, 4. It's a simple path because we haven't repeated any of the edges that are included in this graph. So the path that we created was F, A, B, C, D. And we can see it's got 5 vertices and 4 edges. We're asked what is the distance between vertex C and vertex A. And of course, when you've got a complex path like this, there are going to be multiple paths that get you there. We could go from C to B and B to A. But we could also choose an alternate path. We could go from C to D and D to A. Or we could go from C to E to F to A. Or we could even go from C to E to B to A. When we're asked for the distance, however, we're being asked for the path that has the smallest number of edges, which in this case is 2. And there are 2 paths that give us that distance, either going from C to B to A, or from C to D to A. Finally, we're asked what is the distance between A and D. We can see that the shortest distance is just 1 edge, so the distance is 1. Some more definitions. A circuit is a path that starts and ends at the same vertex. Let's use an example. E to B, B to C, C to D, D to A to B, and B to E. So it ends up where it started. That makes it a circuit. We write a circuit in the same way that we write other paths, simply by identifying the letters that make up the circuit in the order that they appear. A simple circuit is a circuit that has no repeated edges, but it doesn't need to use every edge. As an example, we could start at E, go to B, to C, to D, to A, and back to E. It's a circuit because it ended up where it started, and it didn't repeat any edges as the previous example did. Try this question. We're presented with a path, and we're asked to find the path with a length of 4. We'll start off at B, go to A to F, F to B, and B back to A. We can see that our path has 4 edges on it, and it repeats one of the edges, the edge between B and A. We've drawn the path. Now we'll write it down by identifying each of the vertices that make up the path. B, A, F, B, A. 1, 2, 3, 4 edges. Now we're asked to find a simple path with length 6. I'll start this time at C, C, D, D, A, F, F, B, B, E. I've got 1, 2, 3, 4, 5. One more makes 6. So our simple path is C, D, A, F, B, E, F. Next, we're asked to find a circuit with length 5. Let's go from A to B, B to E, E to C, C to D, and D back to A. So we've got a circuit. It starts at the same vertex where it ends, and it's got 1, 2, 3, 4, 5 edges. So it has a length of 5. And we write it out as A, B, E, C, D, A. Now we need to find a simple circuit with length 3. So a simple circuit means it has to start and end at the same place and not have any repeated edges. The most obvious would be some kind of a triangle. A, F, B, A. It has a length of 3, it's connecting 4 vertices, and has 3 edges. Finally, we're asked to find the distance between vertices A and C. Let's look at the paths that will get us there. We can go A, D, C, A, F, B, E, C, and so on. There are going to be different paths through this because there are a number of different vertices. So now to find the distance, we want the shortest distance between the two. So in this case, it's A to D and D to C, which gives us the distance between the vertices as 2. The key definitions from this lesson are path, simple path, length of path, distance between vertices, circuit, and simple circuit.